All right, welcome back. We today are going to look at more applications from chapters 9 and 10 on rotational dynamics, torque, angular momentum, and also rotational kinetic energy we'll get to today. We'll also have another quiz next Wednesday. Now I'm going to start putting these at our normal class meeting time for the quiz, and so please try to keep that time cleared out for quizzes and exams, since that was our normal meeting time, so that I don't get a lot of emails from people who now have a work schedule that I have to adjust to. And so next Wednesday then, and then I'm going to make it the following Wednesday will be after spring break will be the midterm. And so I'm taking a little extra time to get you used to this new system before I give you a midterm. And so you have that quiz today, Thursday, and then we'll have another quiz next week. Then you'll have a whole spring break week to prepare, knowing how the structure of the midterm will go. And then we'll work from there. All right, so today, last time we're looking at applications of F equals ma and combining that with the principles of torque equals I alpha. And I want to do some more with that today. And a kind of classic example of rotational dynamics is the yo-yo. And so with the yo-yo, we'll make a couple of assumptions. One is that the yo-yo is a solid cylinder of radius r. Now that isn't exactly true, but we can say that it's approximately true. If we were to look at the yo-yo from a side view, we would see maybe something that looks more like this. Not exactly cylindrical, although it has a cylindrical cross-section if you were to look at it from this direction. But it's also wound by string in here. And so that string then, by the time that it's filled up that volume, makes it approximately the same thing as a cylinder. And so we'll also assume that the string is coming out from the tangential outer edge. So in other words, the yo-yo is fully wound when we calculate the acceleration. And so here, let's say the yo-yo has a mass m, is a solid cylinder of radius r, and let's find the acceleration of the center of mass. In other words, here's the center of mass, and so we're going to expect an acceleration of the yo-yo. If it starts from rest, it isn't moving upward, it's moving down, and it'll have an acceleration as it unwinds. And so we know that it's going to be turning this way. So we can draw the forces in. Here we have a tension force. Here we have a weight force. Now you can think for a second as to which force should be larger. We know that it's accelerating this way, so the tension force cannot be equal to the weight force. There must be a difference between them that's equal to mass times acceleration. And that's why it's moving in this direction. So we can then choose the positive direction to be the direction of motion, and we can write the sum of the force equations in the y direction as equaling ma. Okay, and m then is the mass of the yo-yo. A is the acceleration of the center of mass. So then we write this as mg minus t equals ma. Okay, so that's our first force equation. Now, unfortunately, we can't just solve this for the acceleration because we do not yet have enough information regarding what the tension is. And so we can get that tension information from the torque equation. So this is one equation and two unknowns. The unknowns are the tension and the acceleration. And so our second equation then is the sum of the torques equals I alpha. And of course, anytime that we do a torque problem, we need to assign a pivot point. And so I'm going to choose the pivot point for this example to be at the center of mass. I don't have to choose it there. And again, as I did in the last example, I'm going to solve it using the parallaxis theorem a different way. Okay? Like I did with the cylinder rolling down the inclined plane. So I'll do that with this problem too and show that I get the same answer. So there's no magical choice of a pivot point. All right, so choosing though the center of mass as the pivot point, I know what I center of mass is. That's equal to 1/2 mr squared. So I can write then about this pivot point, I see that the weight vector intersects with that pivot point. So therefore, the weight vector is not a part of the torque equation. But the tension force is, because that has a perpendicular radius vector that intersects the tension 90-degree angle. And so we can write then that the torque is the tension in the string times R. That's equal to I, which is 1/2 mr squared, times the angular acceleration. So remember, the angular acceleration is A tangential over R. So we'll write it as A tangential over R, but as we discussed in the last example, A tangential is the same as A center of mass. So you can rewind to that section if you don't remember the argument for that. But that argument is one that we'll be using all the way through these different examples. Okay, and so this acceleration then is the same acceleration as the acceleration of the center of mass. So that we can rewrite this equation by canceling out one factor of R here as TR equals 1/2 mRA. Canceling out a second factor of R, we see that the tension doesn't really even depend on R. It's just equal to 1/2 mA. So now we have a condition then on the tension that can be plugged in to equation 1. So if we take equation 2 here, plug into equation 1, we get that mg minus 1/2 mA equals mA, or mg equals 3/2 mA. M's cancel, and so that gives us A is equal to 2/3 G. So we see a similarity then between this equation and the one that we got last time for the cylinder rolling down the inclined plane. Remember, that was 2/3 G sine theta. And so this one, although it's quite a different problem, has a similar form to it. Now, in a real problem, the radius would change each time that the yo-yo turns, because it would slowly unwind the string that's inside. And so that becomes a much more difficult problem. And we find that a lot in physics, where if you don't make these idealized assumptions, the real-life solution is extremely difficult. And so we're not going to go that far here. As long as we can solve this problem with these assumptions, you'll be fine for any quiz or exam problem that I would give you. But let me do this now using an alternative method. And in this alternative method, I'm going to choose a different pivot point. So here's our tension again. Here's mg. But instead of choosing the pivot point to be at the center of mass, now I'm going to choose the pivot point to be at the edge of the cylinder. Can I do that? Well, sure. And just as long as I'm consistent with my torque equals I alpha equation. However, if I'm rotating this thing about the edge of the cylinder, we know from the parallel axis theorem that the moment of inertia is going to get bigger. It's harder to rotate this thing about the edge than it is about the center, because there's more mass elements at a greater radial distance away. And recall, our parallel axis theorem is I at some distance d away equals I center of mass plus md squared. I center of mass is 1/2 mr squared plus m. Now the distance that we're moving, the axis parallel to itself from the center of mass, is a distance d equals r. So the d that we plug in here is r, so it's just 1/2 mr squared plus mr squared, or 3/2 mr squared. Just like before in the cylinder rolling down the inclined plane problem. We had the same calculation, and we're doing it again here. And so now we can write torque equals I alpha, but the torque now about this pivot point is going to be mgr, because the tension intersects the pivot point, and mg is perpendicular to the radius vector that goes from the pivot point to the point of application of the force. So mgr then equals 3/2 mr squared times a over r. We simplify this by canceling out one factor of r, then a second factor of r, then cancel out the m's. And what we end up getting then is that when the m's cancel and all the r's cancel, we end up getting that 3/2 a equals g, or a equals 2/3 g. So we might say to ourselves, well, gosh, you got this with just one equation, whereas over here it took us 2 equations to get it. But is that really true? No, because in this problem I needed the parallel axis theorem. That was my second equation. And then I could put the new value for I in. But just as is the case in many of these other problems, if you don't put in the right value for the moment of inertia that's consistent with that pivot point, and employing the parallel axis theorem, then you're going to get the wrong answer because you won't have the right value for the moment of inertia. And that's one of the most common errors that I see on exams and quizzes, is that people don't put in the right moment of inertia for the pivot point that they've chosen. Okay, so that's the yo-yo. Let's move ahead and take a look at another example. In this next example, we're going to look at a bucket that is released from a pulley, and the bucket is going to drop down, unwind, as it falls into the well. So let's say that you're getting ready to get some water out of the well, but then you for some reason had to let go. And so the thing starts to accelerate in the downward direction. So then what we have is a big pulley here, and what we can consider to be a point mass. So here's little m and big M for the mass of the pulley. Let's say that the radius of the pulley is r. And what we want to find then is, again, the acceleration of the system. Okay. And so we'll assume there's no friction here. And because of the fact that the mass is falling, but not falling at the acceleration due to gravity, we can conclude that the weight force must be greater than the tension force, because the acceleration is this way. So that's the positive direction. But the acceleration, the angular acceleration of the pulley is this way. Okay, so we can define that as being our positive direction for the torque. Now normally that would be considered to be the negative direction if you use the conventions in the book. And so that's why I don't think that's a particularly good method of solution, because you're putting an artificial negative sign into this problem, where you can just define positive in both cases, to be in the direction of motion, whether it's the direction of rotational motion or the direction that it's falling. Whereas if you chose this direction as positive for the direction of falling in this direction, then you'll get a negative value for alpha and a negative value for the acceleration, which is very confusing. And so this is the reason why I use this method. All right, so our first course of action then, because this is the easiest problem to solve, and we always like to calm ourselves down by doing the part of the problem that's easiest first, because that gives our subconscious mind a chance to start working on the more difficult part of the problem. We'll just use that sum of the forces on this mass equals ma. And again, because it's accelerating in the downward direction, we can write this as mg minus t equals ma. So that looks kind of similar to what we had for the yo-yo, for the force equation. But remember, the force equation does not have anything to do with where the forces are acting. Okay? And so that's where the torque equation comes in, because that's where you get your lever arms, that's where you get your forces that tend to cause a change in spin rate. And so those forces are oriented with respect to the pulley. And so the forces then on the pulley, we have a normal force on the pulley, and then we have a tension force, which is equal and opposite to the tension force on the mass. Okay? And so we can eliminate the unknown normal force by choosing our pivot point to go right through the center of the pulley. And so if we do that, then the torque equation on the pulley, so we're just looking at the pulley now. The sum of the torques on the pulley equals I alpha. So the force equation just involved the forces on the mass. Why? Well, because the forces on the pulley must equal 0 because the pulley isn't going anywhere. So therefore the normal force is already equal to the tension force, and that doesn't really give us any new information for solving the problem. But if we choose this as our pivot point, we don't even have to think about the normal force. We can just say that TR is the torque acting on this pulley, tension times radius vector times the sine of 90 equals I, and we'll assume again that this pulley now is a solid circular cylinder. I center of mass equals 1/2 mr squared. Times alpha, which again, without any explanation, because I've already explained it twice, is just A over R. And so what we end up then with for the tension is that T equals 1/2 ma. And so you may think to yourself, well, I'll just plug in the 1/2 ma here for the tension, and I've got the exact same solution as I had before for the yo-yo. Well, what's wrong with that assumption? Well, these masses aren't the same. Okay, so this is the mass that's hanging that we have here. So that's our little hanging mass. This is the mass of the pulley, which I'll put feet on so that we don't confuse the two masses. So we can't just cancel these masses out because they're two different masses now. Okay, and so that would be an easy mistake to make. So here we've got mg minus 1/2 big M A equals little m times A. So therefore mg equals 1/2 big M plus little m times A. Or the acceleration is equal to little m g divided by 1/2 big M plus little m. So if we have here that big M is equal to, let's say, 4 kilograms, and little m is equal to 1 kilogram, then we could plug in, and this would give us 1 divided by 1/2 times 4, these are in units of kilograms, plus 1 times g. Or that'd be 1 divided by 2 plus 1 is 3, so that would be 1/3 g for the acceleration. Right, so that's how we deal with a problem in which we have a rotating cylinder here, which is being wound up with cord. That's like you would crank. This would be like the wheel that you would crank to bring up water from a well. And then this would be the bucket as it accelerates downward if it's filled with water.